So continuing with examples of geometric series, let's consider another example. So let me rewrite this. This is summation n from 1 to infinity 4 raised to the power n plus 1 over 7 raised to the power n minus 1. So the first thing to notice is that we have to make this start from 0. So again, we have to change the index of summation. So I'm going to say k is n minus 1, because in that case, when n is 1, k would be 0. So then the summation would start from 0. Okay. So if k is n minus 1, that means n must be k plus 1. By the way, suppose your summation was from n starting from 2 to infinity, then your change would be k equals n minus 2. Okay, coming back to this example, let's make this substitution, and when we do that, the summation starts from 0 to infinity, and wherever I see n, I'm going to substitute k plus 1 for it. So I have k plus 1 plus 1, and in the denominator it would be 7 raised to the power k plus 1 minus 1. So that gives me 4 raised to the power k plus 2 over 7 raised to the power k. Now again, I have to split it in such a way that you get a times r raised to the power k. So from k plus 2 with the exponent, I'll get 4 squared times 4 raised to the power k. And in the denominator, it's still 7 raised to the power k. So that becomes 4 squared is 16, and 4, this can be written as 4 over 7 raised to the power k. So this is my a, and this is my r. So a is 16, r is 4 over 7, and this is less than 1. So therefore, the sum can be found, and that would be 16 over 1 minus 4 over 7. And that is simple arithmetic. You can do that, and you should get 112 over 3. And obviously, the series converges. That we could have just said by looking at this r value, but also the fact that we found the sum, that means the series converges. Let's go to final example. So this, let me rewrite this. This says n starting from 0 to infinity 5 raised to the power 3n times 3 raised to the power 1 minus n. So in this case, the summation is fine. It's starting from 0. So the only thing is a little bit of algebra, rules of exponents to be used. So you have to recall your high school algebra. So 5 raised to the power 3n can be written as 5 cube raised to the power n, and 3 raised to the power 1 minus n can be written as 3 raised to the power 1 times 3 raised to the power negative n. But then this becomes, well, 5 cube is 125 raised to the power n times 3, and 3 raised to the negative n is just 3 raised to the power n in the denominator. So again, when we write it in the proper form, I get 3, and then collecting everything with the exponents, I would have 125 over 3 raised to the power n. So n is going from 0 to infinity, so this must be my a and this must be r. So in this case, r is 125 over 3, and that is clearly greater than 1. Therefore, this series diverges. You cannot use that formula to get the sum because r is greater than 1. Okay, now let's go on to the next type of series for which we can find the sum, and therefore we can decide whether it diverges or converges. So these are very special structures. So let's start with this example. So the first thing here is, and you will see it in a few minutes, why we take this approach. So first thing is, you have 1 over k times k plus 1. So what we have to do is use partial fractions to first split it up into two fractions. So this would obviously be a over k plus b times b over k plus 1. So this is my partial fractions. So when I add these two, I get a times k plus 1 plus bk over k times k plus 1. So that means, collecting similar terms, I get a plus b times k plus a must be equal to 1. So this is very simple. A plus b must be 0 and a must be 1. So this term must be 0 and a is equal to 1. So if I know a is 1, then obviously from here b is negative 1. Okay, so I have split this as 1 over k minus 1 over k plus 1. Okay, so this series essentially is sum from 1 to infinity 1 over k minus 1 over k plus 1. So a telescoping series must turn out to have some form of this type, because when we start writing the nth term of the partial sequence, then something interesting happens. So let's write what is Sn. Remember, Sn is the sum of first n terms. So Sn is a1 plus a2 plus and so on till an. Now let's write out these terms. So a1 means the first term by putting k equals 1. So that means I would get 1 minus 1 over 2. Then, so this is a1. So now I'm going to a2. So I'm going to put k equals 2. So I'll get 1 over 2 minus 1 over 3. Then the next term, a3. So k is 3. So that would be 1 over 3 minus 1 over 4. So I can continue this way, and let's write down the last term. So an would be 1 over n minus 1 over n plus 1. Now the interesting thing here is that this kind of a sum telescopes in this following sense. this half cancels with this, then this negative 1/3 cancels with this. So it just telescopes like dominoes and keeps going, canceling till this guy gets cancelled as well. So all that you are left is the first term and this last term. So Sn is actually 1 minus 1 over n plus 1. So we wanted to find the sum of the series, which we now know very well. It's simply limit n going to infinity of Sn. So what is the limit of Sn, which we just found to be 1 minus 1 over n plus 1? That is obviously 1 minus 0, because this guy just goes to 0 as n goes to infinity, which is 1, a very nice number. Therefore, this series converges. Let's look at one more example. Now this one looks a little fancy, but if you remember the properties of logs, then this is actually nothing but ln of k minus ln of k plus 1. Ln of x over y is ln x minus ln y. So that's the idea here. So this is my ak. So if I were to find Sn, which is a1 plus a2, sum up all the way till n terms, then we hope that something nice shows up. So let's write a1. So that is obviously ln of 1 minus ln of 2. K is 1. So ln 1 minus ln 2 from here, from ak. a2 would be ln of 2 minus ln of 3 plus, and if we keep going, our an would be ln of n minus ln of n plus 1. Again, if you look at the pattern here, very conveniently, this ln2 cancels this ln2, this ln3 is going to cancel the ln3 coming from here, and it will keep canceling till it cancels this guy. So we're going to be left with ln of 1 minus ln of n plus 1. Ln of 1 is 0. So that means it's negative ln of n plus 1. So if we are looking for the sum of this series, then I have to find the limit of Sn sequence. So that means limit of negative ln of n plus 1. But ln log is a function that looks like this, goes to infinity. So as n goes to infinity, this guy is going to negative infinity. So therefore, this diverges. So you notice that telescoping series are very special kind of series which behave in this very nice way, so that Sn can be found in a closed form. So once you can find Sn as a function, you can take a limit and decide whether it converges or diverges. So to recap, these are special cases where we can decide on the convergence, and not only that, but also find the sum. But then of course, most series we will not be able to do it, and we'll have to settle with the information whether it converges or diverges.